Hi there, it's me, Dane Quinn. I'm at the University of Akron, and today I'd like to talk about scalar reduction of vector equations. This is a really important lecture because everything that we do in kinematics will start with vector equations and ultimately reduce them to a set of scalar equations. So we really need to talk about how to do that. Again, our loop closure equations that we obtained from the mechanism and from looking at the kinematics are composed of vectors. So here over on the right, I have a 4-bar linkage. We see an input link in orange, and then a connecting link and an output link, and then the ground link in blue. So again, this is the loop closure equation. We might start here, go to here and there, and ultimately that's got to be equal to this vector in the ground and then the output link. So again, this is our loop closure equation that we obtained from looking at the kinematics. So now, how do we get to scalar equations? Well, this is a vector equation. So it contains two independent quantities. There are lots of ways of sort of getting that, but ultimately there are two independent scalar equations built in here. So one of them might be the following. Let's look at the components in the j direction, right? So the component of this orange vector in the j direction is this. And then actually, if we look at the components in the I direction, right, maybe it looks like that, then that could be a known quantity. But then the loop closure equation then essentially represents these other two unknown vectors. So to this, we might add a component like so in the j direction, and then a component like this in the I direction. And then that's got to be equal to, well, in the I direction, this component in the ground, fairly large magnitude, and it actually has no component in the j direction. Finally, that has to be equal to, in the I direction, this component, or in the I direction here, this component. So again, these orange components are known. The red or purple components are unknown, and the blue component is known, right? So we're basically looking for these vectors so that everything in the j direction adds up and everything in the I direction adds up. So that would be two scalar equations. Now, alternatively, I could say that this loop closure equation has these two vectors equaling these two vectors. So I could look at, for example, the magnitude of the resultant. So the magnitude of this vector has to be equal to the magnitude of that vector. And the direction has to be the same. So again, there are a number of different ways of coming up with these scalar equations. We can look at components, and not just in the I and j direction. We'll find that looking at components in other directions will be useful. Or we could take magnitudes, we can take directions. There are lots of different things we can do, right? But for simple, single degree of freedom mechanisms, this one vector equation gives me two scalar equations and two unknowns. So for example, in the 4-bar linkage that we've shown here, the unknowns would be the directions of these unknown connecting and output links. Right? So we'd have to find the correct direction of these two links so that these components match up. In general, the scalar equations contain all of the unknowns, leading to a big set of simultaneous equations that must be solved. Right? So, fine, right? But the problem is that this is complicated. If you remember from your algebra class, right, when we have simultaneous equations, we have maybe two equations, and each equation has unknowns, and we have to go through and eliminate and solve. And again, that whole procedure is just often complicated. More importantly, we may only be interested in a single output variable. So, for example, in this 4-bar linkage, we may have the input link and its angle as known, and we may be interested only in the output angle of link 4. We may not care about link 3, but we may have to go and solve that along the way. So again, these simultaneous equations, right, they can be complicated, and we may end up doing and solving for things that we don't really care about, but we have to solve them along the way. So part of today's lecture will be about reducing the complexity as much as possible and maybe writing just single equations in terms of single unknowns. But let's look at how we will formulate these kinematic equations. Right, so here I have a mechanism. This is actually equivalent to a slider crank. I have another lecture on that. So I have a bar, and this will be link 2, and it's assumed to be at some angle, and then we have a collar at A that's pinned to the output link L3. Right, so as this input collar, or as this input link moves around, right, the collar slides back and forth, and then the inclination of this output link can change. So the first thing to do, the first thing that we always do, is try to identify the loop closure equation. So in this case, we see that the vector from O2 to A plus the vector from A to O3 equals the vector from O2 to O3. So this is going to be our loop closure equation. Again, we can write that as position of A with respect to O2 plus the position of O3 with respect to A is equal to the position of O3 with respect to O2. Right? So again, this is A with respect to O2. This is O3 with respect to A. And then this is O3 with respect to O2. Now, the next step is to go and actually figure out what these things are. So let's look at the position of A with respect to O2 first. Now, this bar moves around, so the orientation of this vector can change. It is known, right, because again, it's going to be assumed to be our input link, but we'll write that as of direction I2, right? So we'll define I2 and J2 to be fixed in link 2, so that I2 is the direction of this link. Now, the length of this vector is also known, or unknown, right? So I'll call that x. As a result, this vector is x in the I2 direction. So here I'm going to write in red things that are unknown, green is the input, and then in black we'll have things that are known. So for example, the vector from O3, well, from A to O3, that has known length, L3. The direction, however, is variable and unknown, right? So we'll define this direction as I3 and J3, so that the direction here is in the I3 direction. Finally, the vector from O2 to O3, well, that's going to be known. because it's just fixed in the ground. So I'll define I and j fixed in the ground. And this is just L1 in the I direction. So here, this is our vector loop closure equation. Some unknown magnitude in the I2 direction plus a known length in the unknown I3 direction has to be equal to a known vector, L1I. We still need coordinates to describe these changing directions. So here we'll define this angle, theta 2, as the angle between I and I2. Then we'll define the clockwise rotation of I3 and J3 with respect to I and J with the angle theta 3. So notice that x and theta 3 are unknown, theta 2 is the input, and then L1, L3 are known lengths. So in this, we see that theta 2 is the input, and x and theta 3 are unknown. So what's the easiest way to obtain scalar equations from this vector loop closure equation? Well, it's taking components in the I and j direction. So we want to write I2, and we'll go ahead and do J2 as well, and I3 in terms of I and j. So in particular, I2 is cosine of theta 2 in the I direction plus sine of theta 2 in the j direction. J2 is minus sine of theta 2 in the I direction plus cosine of theta 2 in the j direction. And I3 is cosine of theta 3 in the I direction minus sine of theta 3 in the j direction. Again, because theta 3 is clockwise, positive. J3 is sine I plus cosine j. Okay, so essentially I will take these directions, I2 and J3, or I2 and I3, put them into the loop closure equation, and then pull off components. Right, so again, we have x, and now I2 is cosine I plus sine j. L3, I3, cosine I minus sine j equals L1 I. So I need to pull off components in the I direction. One way of doing that is to dot this whole equation by I, because of course I dot I is equal to 1, right? So we'll pull off this component. I dot j is equal to 0. And so that goes away. And we see x cosine of, actually I'll go ahead and color these as they're known and unknown. X cosine of theta 2 plus L3 cosine of theta 3 equals L1. And then j dotted with the loop closure equation gives me my second scalar equation. Right, so that's going to be x sine of theta 2 plus, actually minus now, minus L3 sine of theta 3 equals 0, right? Because there's no j component on the right-hand side. So from this vector equation, we're able to obtain two scalar equations. So again, we have two equations and two unknowns, x and theta 3, and they both appear in both equations. So this is an example of simultaneous equations. Well, Okay, we just have to solve those. Here they are again, rewritten nicely. These are combined. So we must eliminate one variable and substitute it into the other equation, leaving a single equation with a single unknown, which can then be solved. So I'm actually not going to solve these, but I do want to get down to those single equations and single unknowns that can be solved. Right? The solving of them isn't just, it's algebra. We've done similar things in the past, and really what I'm focusing on today is just getting down to a single equation that we can solve for a single unknown. So first off, let's try solving for x. Which means that we need to eliminate theta 3. So I'm going to solve one of these equations for theta 3, and then I'm going to take that and substitute back into the other equation. So the one that I'm going to choose to use to eliminate theta 3 is the second equation. Right? So basically, I'll solve this, and we see that theta 3 is equal to the inverse sine of x sine of theta 2 divided by L3, right? So again, I just solved this equation for sine of theta 3, which is x sine divided by L3, and then took the inverse sine. So then I want to take that value of theta 3 and put it back into this equation. So when I do that, I get x times cosine of theta 2 plus L3 cosine of theta 3, right? But what was theta 3? Well, theta 3 was the inverse sine of x times sine of theta 2 divided by L3, and that's got to be equal to L1. Okay, so now we have a single equation in terms of x that we can solve for. But quite honestly, this is not something that we really want to think about doing because, I mean, we can. It's possible, right? Maybe you even know how to do this, right? But we have cosine of inverse sine. Well, that has to be somehow reduced in terms of x, and it's not the greatest thing in the world, right? So actually, we're going to talk about ways of rewriting and reformulating this to be more convenient, right? But for now, this is what we get, right? So you have to go and solve for x. All right. This is a single equation in terms of a single unknown, though, right? So we did what we were trying to do. So now let's go and look at the other one. Let's solve for theta 3, which means eliminate x. So I'll actually use this same second equation to begin with, right? And we'll say that x is equal to, well, just solve for x. L3 sine of theta 3 divided by sine of theta 2. Right? So I can take that, introduce it into this first equation, and get the following. Well, x, which is L3 sine of theta 3 divided by sine of theta 2 times cosine of theta 2 plus L3 cosine of theta 3 equals L1. This is a little bit easier to solve. Turns out, well, we could use some angle addition formulas and that kind of thing, and we can go and solve this for theta 3. But again, we've done what we wanted to do, right? We developed a single equation in terms of theta 3. Just like up here, we have a single equation in terms of x. And we got that by taking our two scalar equations, doing some algebra, eliminating one unknown, and finding a single equation in a single unknown. This procedure, though, it's a little bit complicated. There's a lot of algebra involved, right? So I'm going to show you a different way, slightly clever, of going from our vector loop closure equation down to a single equation with whatever unknown that we are interested in. So with the right procedure, we can directly reduce vector equations to a single scalar equation with a single unknown. And as a result, we don't have to worry about taking simultaneous equations, solving for one, substituting back in. It just becomes a much cleaner and less tedious approach. And we do that by directly eliminating the unwanted variable. And again, if I have a vector equation with two unknowns and I eliminate the unwanted variable, whatever's left is a single scalar equation with a single unknown. It's kind of like Sherlock Holmes, right? If you eliminate everything that you don't want, then what you're left with is the thing that you want. So let's do that procedure. Let's go through that on our problem again. I'll remind you of the loop closure equation. It was x in the I2 direction plus L3 in the I3 direction equals L1 in the I direction. So I'm going to do this twice. Again, I'm going to come up with an equation for x directly. I'll come up with an equation for theta 3 directly. So again, solve for x. Well, don't think about solving for x. Think about eliminating theta 3. All right, so how can I eliminate theta 3 from this vector equation? Well, where is theta 3? It's in this I3 term, right? So let me rewrite this. L3 I3 is equal to L1I minus xi2. If you notice, the magnitude of the left-hand side is known, right? Because even though the direction is not known, right, the magnitude is simply L3. So that means that the magnitude of the right-hand side is known, and it's equal to L3. So what I want to do is take the magnitude. Take the magnitude of both sides. And in particular, I'm going to dot each side with itself. L3I3 dot L3I3 is equal to L3 squared. So I'll actually get the square magnitude. So writing that out, L3I3 dot L3I3, that's the magnitude of the left-hand side, has to be the magnitude of the right-hand side. So I'll just dot that with itself. So L3 squared is on the right-hand side, or the left-hand side. All right, so maybe I'll go through and color that red just so we can highlight the unknown variable. And as a result, if you work through this, you end up with L1 squared minus 2 L1 x times I dot I2 plus x squared. Again, take these dot products, I get L1I dot L1I, right? I have an L1I dot minus xi2. That's one of these. I have another one from here, and then this is where the x squared comes in. So as a result, we end up with the following equation. L3 squared equals L1 squared minus, and I dot I2 is just cosine of theta 2. And we finally end up with this quadratic equation for x. Turns out that this is exactly the same thing that we would get if we reduced this equation that we got previously. But I think you'd have to admit, this getting to here is much easier than getting to here and then reducing this to a form that we can write it as quadratic in x. So this procedure here, focusing on eliminating the unknown variable, really does simplify the algebra considerably, especially if we're only interested in x, for example. Now, what do we do if I want to solve for theta 3? Well, I'll go back to the loop closure equation. Right? So we see that x in the I2 direction plus L3 in the I3 direction equals L1I. So if I want to solve for theta 3, again, don't think about theta 3. Think about how do we eliminate x. If I do that, then the only thing that's left will depend on theta 3. So notice that this vector, x in the I2 direction, is the only place that x appears. And it has known direction. So how can I get rid of a vector x in the I2 direction? Well, I can take a dot product. I can take, in particular, the component in the J2 direction. Because xi2 dot j2 equals 0. So if I take the component of this entire equation in the j2 direction, this term goes away. So let's do that. Seems like a good idea. So we'll take j2 and then we'll dot everything. xi2 plus L3 I3 equals L1I. So again, j2 dot I2 is equal to 0. So that goes away. And we're left with L3 times j2 dot I3 equals L1 I dot j2. So when I do that, I end up with the following. And you can go back and look at our coordinate transformations and do these dot products. We have L3 sine of theta 3 times cosine of theta 2 plus cosine of theta 3 sine of theta 2 equals L1 sine of theta 2. So this becomes our single equation on theta 3. And in fact, it's exactly the same as we got here. So this idea of working with the vector equations directly can really simplify the algebra that's involved. Now, once you get one of these, you can actually go back to the scalar components, right? So say I knew theta 3, you could solve for x directly. Say I knew x, right? You could use this and solve for theta 3. So again, once you know one of the coordinates, you can always go back and find the other unknown. But this makes it much easier to get down to that single equation and single unknown. So let's summarize these steps for simplifying vector loop closure equations. And again, I'm going to focus on the things that we want to eliminate. So for example, in this previous problem, we saw that if we wanted to solve for x, we want to eliminate theta 3. Solve for theta 3, we want to eliminate x. So it's the elimination part that's really the important thing to focus on. So if I need to eliminate an unknown direction, here I have a 4-bar linkage, right? So the loop closure equation could be L2, I2 plus L3 equals L1I and L4I4. And I've already given you all these directions and angles and that kind of stuff. Let's assume that theta 2 is the input, theta 3 and theta 4 are the outputs. So I want to solve for theta 4, but again, really what I want to focus on is eliminating theta 3. So it's this term that I want to get rid of. Well, to do this, we want to isolate those unwanted directions. So for example, here, this loop closure equation, L3, I3 is the thing I'd like to eliminate. So I'm going to write that in terms of the other equations, right? So I might go from this point to this point and over and then back up, right? So really that amounts to L3, I3 is minus L2, I2 plus L1, I plus L4, I4. So again, I've isolated this unknown direction, and then everything on the right is independent of theta 3. And in particular here, maybe I4, theta 4, is the thing that I'm trying to solve for, while this is the thing I'm trying to get rid of. So when I do that, essentially I want to recognize that the length of this vector is independent of theta 3. So I'll take the magnitude of this vector, which is L3, and I'll take the magnitude squared in particular. So I get L3 squared is the magnitude of these, it's the magnitude of the resultant vector from these three components. Right? So basically just take the dot product of each side with itself. L3, I3 dot L3, I3 equals the magnitude of the right-hand side. So I'll take L2, I2, L1I, L4, I4, and I'll dot that with itself. Right, Oakley? Oakley agrees. So, in doing so, this left-hand side becomes L3 squared. And the right-hand side, well, so there's, a bunch of dot products and things to do. I'll just write out the answer for you. You can pause this video and go through and work this out for yourself. L1, L2, cosine of theta 2. I get an L1 squared. I get 2 L1, L4, cosine of theta 4. I have an L4 squared. And then I have 2 L2, L4. Turns out this is cosine of theta 4 minus theta 2. And in this, my unknown variable is isolated. So I still have to solve this, but I've immediately reduced down to one equation and one unknown. It turns out that this equation actually is relatively famous in kinematics. It actually has its own name. It's Freudenstein's equation. Clearly German. And we got it by simply isolating and eliminating the unknown angle theta 3 from the vector loop closure equation. Right, so this really is, it's a very nice way of simplifying down to one equation, one unknown. What happens if we want to eliminate an unknown magnitude? Right, so here we have a second mechanism. Right, again, this turns out it's an inversion of a slider crank mechanism. And here, the loop closure equation is L2I2 plus Z in the I3 direction as L1 in the I direction. All right, so our loop closure equation might go from there to there, there to there, equals there to there. So how do we do this? Well, L2 I2 plus ZI3 equals L1I. And I recognize that I want to eliminate this angle or this length Z. Maybe I'm trying to solve for this angle theta 3. So I take a component of the equation in a perpendicular direction. So in this case, I would dot this equation with J3, perpendicular. Now, you might say, oh, but that's no good because it eliminates the theta 3 term here. And that is true, but since this term that I'm dotting with depends on theta 3, it actually gets reintroduced into these two pieces. And so when you work this out, you get L2 sine of theta 2 plus theta 3 equals L1 sine of theta 3. And again, single equation in terms of the unknown that we're interested in, because we eliminated the unknown that we weren't interested in. So again, this procedure, these two steps here, can really be used to simplify loop closure equations. And the focus is on getting rid of the things that you don't want. So admittedly now, at this point, you actually have to go and solve these equations, right? But this is a nice way of coming up with equations that are much easier to solve than our two simultaneous equations and two unknowns, for example, that we saw earlier. So a lot of the problems that I solve, I will be using this approach. And as we move to velocity and acceleration, this second step here, eliminating unknown magnitudes, will be what we'll primarily be focused on in solving equations. So this ends up being really useful to quickly solve for velocity and acceleration terms. Okay, that's it. Oakley and I say goodbye. Thanks a lot. Say goodbye, Oakley. Oakley, say goodbye. Say goodbye.